Welcome everyone to today's webinar, Best Practices for FPGA and Software Integration in MPSoC Architectures. We're thrilled to have you join us for our deep dive into optimizing real-time efficiency through FPGA and software co-design in MPSoC high-performance embedded systems. Before we begin, let's go over some quick housekeeping items to ensure a smooth experience through today's webinar. We will have a live Q&A session at the end of the presentation, so I do encourage you to submit your questions and we will be answering them at the end. Feel free to type them in as they arise, and should you encounter any technical issues or need any assistance, just send a message through the chat and our webinar admin team are here and we're ready to help you. So who is Fidus? Well, we were founded in 2001 and we have since grown into a 150-person all North American embedded system services company. We serve all industries and markets and have 3 brick and mortar locations in North America, 2 in Canada and a US home base in the Silicon Valley. We've been working with embedded systems since 2002 and we're the proudest of our repeat customer rate. Close to 95% of our customers return year over year with new projects and new business. A real testament to the quality and efficiency of our work and our commitment to doing it right the first time. We have an exceptionally strong partner ecosystem with strong partnerships with AMD, Altera, formerly Intel, Analog Devices, and Lattice, to name a few. Most recently, this past July, we were thrilled to have been announced Partner of the Year by AMD. In our first decade, Fidus did a ton of varied AMD Xilinx related work. And so in 2011, Xilinx asked Fidus to become their first ever Premier Design Services member in North America. To this date, we have collaborated closely on opportunities and trained together on the latest technologies, such as Versal and their latest Embedded Plus architectural series, all with the end goal of helping our joint clients get their solutions to market as accurately, quickly, and smoothly as possible. As a full services electronic systems design firm, our professionals and engineers cover a multitude of service disciplines, including FPGA and ASIC design, embedded software, hardware, signal and power integrity, verification, and many more. We help our customers by supplying some of these expert skill sets directly or by managing the complete project from start to finish. Now I'd like to introduce our 2 expert speakers. Chris Tippett is an FPGA designer at Fidus with 5 years of experience in FPGA development across industries like semiconductor and audiovisual. He's skilled in Verilog and System Verilog and has worked with AMD, Intel, and Microsemi platforms. Joining Chris for the Q&A is Jeremy Brooks, a senior embedded software designer with over 20 years of experience in embedded software architecture for sectors like aerospace, defense, and IoT. His programming expertise across various hardware platforms makes him a key resource for today's session. All right, Chris, over to you to get us started.
Thank you, Alicia. Hello everyone, my name is Chris Tippett, an FPGA designer with Fidus Systems, and assisting me with this topic today will be Jeremy Brooks, who is a senior embedded software designer. This webinar will dive into the importance of FPGA and software integration, highlighting how critical FPGA and software co-design is in order to achieve the best results possible.
Hello, my name is Jeremy Brooks. I am a senior embedded software developer at Fidus Systems. There are many things to consider when designing an effective and efficient solution using the combined resources available on MPSoC devices, including programmable logic, real-time processing units, application processing units, and graphical processing units. Coordination between the various FPGA and software resources is essential to producing an effective design. In today's presentation, we will be discussing architecture considerations for creating an efficient design using both FPGA and software resources, common interfaces used to coordinate system functionality between the programmable logic and software, best practices for coordinating FPGA and software design, and finally, we will discuss some practical tool and project examples.
Our first topic is going to be about architecture considerations. Both the software and the FPGA development needs to be architected together to ensure the best system performance. First, we will take a look at the concept behind a multiprocessor system on chip to see why it is important that FPGA and software work together, and then look at some considerations that should be made on an architecture level, including what functions are better suited for software, what functions should be done in the FPGA, and to tie those together, what interfaces will be used so that software and the programmable logic will be able to interact with each other.
An SoC, or system on chip device, typically integrates a processor with other components such as programmable logic, memory, and I/O devices, among many other integrated components. An MPSoC, or multiprocessor system on chip device, will integrate multiple processing cores along with other components to optimize the desired application. One example of this is the Zynq Ultrascale Plus MPSoC, which contains a dual-core application processing unit, APU, a dual-core real-time processing unit, RPU, and programmable logic. The processing subsystem, PS, and the programmable logic, PL, have many interfaces which can be used to coordinate functionality between the two subsystems. These types of devices highlight the importance of software and FPGA co-design in order to make the most of its resources to achieve the system performance. There are many device offerings such as the aforementioned AMD Zynq Ultrascale Plus or the Intel Stratix 10SX SoC, just to name a few. When discussing the coordination of system functionality between the FPGA and software, it is important to identify those functions which are better suited to be handled in software versus those which should be handled by the FPGA. Some examples of functions that may be handled more effectively by software include user interfaces, such as graphical user interfaces, command line interfaces, menu-driven interfaces, and sensory interfaces. Register configurations used to control hardware or the FPGA by setting registers based on the intended use case. Functions or calculations that are not timing critical due to the inconsistent delays in a software system. For example, extracting an image from a system memory or parsing a text file. Any high complexity state machines or functions that would otherwise result in huge resource utilization in the FPGA. Any functionality which may require updates, as changing software is less costly both in time and money versus modifying the hardware or the FPGA design.
Now for some examples of functions that are better suited for the FPGA domain, including video processing. FPGAs are very good at performing repeated tasks at high speeds, such as processing continuous streams of video data. Calculations or sequences that happen in parallel are also strong contenders for an FPGA, since FPGA code is executed in parallel. FPGAs have very short and predictable delays, so time-sensitive interrupts is another good contender for the FPGA domain. Using logic in an FPGA to respond to a certain scenario and generate an interrupt based on an error condition can be crucial to make sure the performance requirements are met for the system. This FPGA-generated signal can then be used within the FPGA code to handle the situation directly or be passed to software to handle. FPGA's short and predictable delays also means that they are good at handling real-time functions. For example, monitoring vitals in the medical field, processing images in the automotive and aerospace industries, and managing high bandwidth wired and wireless telecommunications. To tie the processor and programmable logic together, how they will interface with each other is very important. Defining the interfaces early on helps set the groundwork for co-design between software and FPGA developers. Having a plan from the early phases of development helps to ensure that the design will have the best performance possible and minimizes surprises later in the development cycle, which ultimately speeds up the development process.
Next, let's discuss those software and FPGA interfaces and how they can be used to tie things together. As we have discussed, in many cases, it can be quite beneficial to assign system functionality between the software and FPGA depending on the system requirements. In order to accomplish this, coordination between the software and FPGA is therefore critical. The interfaces often used to support the coordination between software and the FPGA include monitoring and updating memory mapped control and status registers accessible by both the software and FPGA, monitoring and updating GPIO pins routed between the programmable logic, PL, and processor subsystem, PS, generating and handling interrupts between the PL and PS, direct memory access, DMA, transactions used to transfer blocks of data between the PL and PS. When multiple processors are available, as is the case on the Zynq Ultrascale Plus, coordination between the processors is also required. There are a number of ways to coordinate the multiple processors in an asymmetric multiprocessing system, One possibility is to use the OpenAMP framework, which provides methods to coordinate task management on a multi-processor system. OpenAMP will be discussed in more detail later. For many designs, the ability for software to interact with the FPGA via control and status registers is critical for system performance. Being able to manage these registers in the FPGA using software allows for more possibilities in the design, such as the final product can be more flexible and user-friendly, allowing for easy configuration through an intuitive user interface, supports rapid switching between operating modes by efficiently configuring the necessary FPGA registers based on user inputs, optimizing performance and responsiveness. Real-time status and error detection inside of the FPGA can instantly notify software which can handle the event appropriately. Software can provide commands or requests to the FPGA to access these registers. Common interfaces used for this are AXI or PCIe. FPGA and software designers working together to plan the layout and format of the registers is critical, since that can greatly decrease the complexity of the interface requirements. Interrupts and polling is another example of how interfacing between the FPGA and software can provide complete solutions. Interrupts are used to deal with events in real time. Interrupts can occur at any time. The FPGA can drive an interrupt signal, which the embedded processor will handle right away. Very useful if you don't know when the flag condition might occur, or if it is a condition that must always be urgently handled. Polling, on the other hand, is the act of software checking the status of a signal every certain number of clock cycles. Polling is simpler than interrupts, since polling does not require lower levels of the operating system to properly connect with interrupt handlers. However, polling can use more resources in the embedded processor, as it is constantly using cycles to check the status of the signal. Polling is generally used when the software needs to respond to events that aren't time sensitive. Direct memory access, or DMA, is used to transfer large blocks of data with limited involvement from the CPU. Using the AXI DMA allows software to transfer and receive large blocks of data from the FPGA. At Fidus, we have extensive experience using the DMA engines to streamline data movement between the software, FPGA, and hardware. A good example of using DMA for moving large blocks of data would be software moving video frames between memory and FPGA processing blocks, such as a video codec unit or a video mixer.
Now let's discuss FPGA and software co-design best practices. In FPGA and software co-design, it is important to engage all team members early in the development cycle and to have frequent integration points to ensure that each member stays aligned with the final goals. The Agile workflow is an example where this is very important in order to complete features from start to finish with as little backtracking as possible. In order to deliver complete features, FPGA and software designers should work together to ensure the best results possible. Early involvement for each team member is important, regardless of any dependencies that a member may have on previous work being completed first. Early engagement is critical in keeping goals aligned from the beginning, which also helps to minimize any future issues that could eat into development time and budget restrictions. Having frequent points of integration is another thing that we do in order to deliver quality results. The flow of the design is kept under control by doing things like defining the register map early so that both the software and FPGA developers are on the same page. Frequent code drops allows for regular feedback, which is important for making small adjustments throughout the design process, since it is better to make small corrections throughout development than to go off track and require larger changes later on. In many situations, small changes to the FPGA design can greatly reduce software complexity and support standard API, library, and driver reuse. The Agile workflow is a common flow where applying these strategies can make the entire design process flow smoothly from beginning to end.
Now let's look at some practical examples to show how software and FPGA co-design can be applied. Some practical examples we will look at include tools that are used to help bridge the final solution of software and FPGA design, a more in-depth look at the Zynq Ultrascale Plus MPSoC, and finally, we discuss a real-world project example which combines FPGA and software development into an integrated solution. A prime example of a co-design tool is the Vivado suite for AMD devices. This suite also serves as a solid reference for other platforms, such as Intel's Altera tools. Vivado is used to generate an FPGA design. One of the outputs of Avado is an XSA file, which is used by AMD software tools to extract information about the FPGA hardware. The XSA file includes the FPGA bitstream, which is loaded into the device by software. On the software side, the Fidus software platform and AMD's Petalinux tools offer support to build bare metal, FreeRTOS, or embedded Linux distributions depending on the software requirements of the design. At Fidus, we have extensive experience in configuring the ideal software platform to meet the system software requirements, ensuring compatibility with available hardware, integrating existing drivers, generating device trees, and building applications to deliver a complete solution. Looking at an MPSoC device, the AMD Zynq Ultrascale Plus MPSoC lineup is an excellent example where software and FPGA co-design is paramount. As previously discussed, the Zynq Ultrascale Plus MPSoC has a processor subsection, PS, and a programmable logic section, PL. The PS consists of an APU, in this case a dual-core Cortex-A53, and RPU, in this case a dual-core Cortex-A9. Depending on the application requirements, functions can be performed by the PL, APU, or RPU. The APU can be configured to run Linux, FreeRTOS, or bare metal, whereas the RPU is usually configured to run with either FreeRTOS or bare metal, depending on the application requirements. The difference between FreeRTOS and bare metal is that FreeRTOS provides drivers and an operating system to simplify development, while bare metal has much less overhead and has API libraries to support the bare metal operation. OpenAMP can be used to coordinate the APU and RPU. The APU can load both the PL and RPU using OpenAMP at real time, giving the system design flexibility on where certain functionality will take place. OpenAMP has features including Remote Proc and RP Message, which simplify inter-processor coordination and communication.
And finally, a project example where we have tied all of our FPGA and software co-design experience together at Fidus is our Sidewinder product. The Sidewinder is the world's first AMD Zynq Ultrascale Plus ZU19EG storage accelerator PCIe card. This product is the result of what Fidus designers can achieve when working together on a product. Some applications of the Sidewinder that highlight FPGA and software coordination include, but are not limited to, leveraging NVMe drive technology and NVMe over Fabrics IP. Sidewinder can decimate the latency associated with accessing mass storage devices, for example SSDs. Clustering the Sidewinders to create massive storage arrays, you can leverage parallelism for workload acceleration to make things even faster. Whether accelerating financial transactions or data center workload algorithms, Sidewinder's Zynq Ultrascale Plus can be optimally partitioned to accept, crunch, and return both data and decisions faster than any previous model. And if the Sidewinder is not exactly what you need, Fidus Systems is ready to customize Sidewinder to meet your needs. We have in-house experts in hardware, FPGA, software, signal integrity, and PCB layout to help accelerate your product design. That concludes myself and Jeremy's part of this presentation. We hope you have learned a lot about the importance of FPGA and software co-design, and we will now pass things back over to Alicia.
Okay, so just a quick reminder to all of our attendees, if you do have any questions, make sure to pop them in down on the Q&A option down there on the panel. But we do have one in so far. Here, this is from Rakesh. So I'll leave it to you, Chris, or Jeremy to answer, to decide amongst the two of you. So the first question is, with future SoC technologies emerging, how do you think the importance of software and FPGA co-design is going to change?
Yeah, I can answer that one. So the importance of software and FPGA co-design is going to remain as important as ever for any future emerging technologies. I can provide an example of this with a new platform, AMD Embedded Plus. It uses an AMD Ryzen embedded processor for the software side, along with a AMD Versal AI FPGA on the programmable logic side. So this new platform really showcases that software and FPGA integration is going to remain as strong as ever in order to provide any of the best up-to-date solutions going forward.
Thank you. Jeremy, do you have anything to add to that?
No, I mean, ultimately, the you know the FPGA and software both have their advantages in a system, right? And you'll always find that certain functions are better performed by software, certain functions are better performed by the FPGA. and deciding which one is best is always going to be imperative to creating a good solution.
So is there a particular way that you would recommend to people for testing which way is best or which, discipline to use?
Well, ultimately, I mean, you need to look at the requirements of the whatever function you're trying to achieve, right? And based on that, you can decide, okay, well, this makes sense to do in the FPGA because it's a lot of easy, simple processing or something that doesn't require a lot of user intervention. Whereas, in certain cases, like if you need configuration that requires user intervention, um, it makes more sense to do that type of function in the software.
Thank you. Okay, I've got another question here from Peter. Could you give us some examples of common issues you've run into that are dependent on each other as software and FPGA developers?
Um, I could probably feel that one. I mean, for for myself, I find it's very important to have software and FPGA involved at an early stage in the project, in order to um, make sure that you can easily integrate the software to the FPGA later on in the project. So by that I mean I found in the past by having software involved early in the project and coordinating with the FPGA, you can often um, gear the FPGA design towards and it's easy to change the FPGA design in certain instances to make it a lot easier for software integration. Whereas sometimes if you don't have that involvement, what will happen is the FPGA will make a change that then requires a lot of software work in order to accommodate that change, right? So for me, it's you need to really be involved in the at the beginning of the project, both teams working together in order to facilitate the driver development or whatever software you're developing.
Thanks, Jeremy. Chris, did you have anything you wanted to add to that?
I don't think anything new, but yeah, I think Jeremy really covered about how what is paramount is just communication in general between the software and FPGA designers to make sure that your views align with how the final product is going to be achieved.
So important. So this is from Grace, and you've probably repeated, this may be a little bit repetitive, but if software alone can perform the functions necessary for a design, then why is the FPGA even necessary?
Yeah, I'll talk about that one. So it may be true that there are some solutions that can be done entirely in software, but when it comes to more complicated solutions that may rely on things such as like time, if you want time-sensitive responses, or could be more resource hungry, that's where the coordination between the software and the FPGA side can really come in handy. I can provide an example of like a generic video processing solution. I won't get into too much detail, but in software, some of you may be familiar with OpenCV libraries, and that's libraries that can handle all sorts of video manipulation methods. You can take your video and you can apply filters, you can resize the video, analyze the contents, and do all sorts of things with the video. However, doing all this in software can come at the cost of using up the valuable execution cycles in the CPU, which means that video might not be processed very smoothly, especially with higher frame rate or higher resolution content. The FPGA, on the other hand, is very good at handling large amounts of parallelism for processing video, and it will allow it to process the video without compromise, like the software might struggle. So for tasks like this, it's usually best to let the FPGA kind of offset the software, so that the software can handle other tasks such as, managing registers or monitoring signals.
Fabulous. Thank you. Jeremy, do you have anything to add to Chris's response there?
No, I think he handled that well.
Okay, excellent. Okay, moving on. I have one here from Hassan. How does the processor help in projects with the FPGA fabric?
I can handle that. So ultimately, I find that the FPGA fabric for complex operations can use up a lot of resources, and in some instances, the processor or the PS can more easily make intuitive decisions that the FPGA would require a lot more resources in the FPGA, and therefore I find the coordination between the two, um, as we've been kind of gearing this presentation towards, is that in certain instances the processor is just better able to handle certain applications, and whereas the FPGA would require too many resources in order to accomplish those tasks.
Excellent. And actually, Hassan has just written a follow-up. So does this FPGA SoC incorporate in most of the technology we do have today? If not, then will it do so in the future? He'd like to know the role of FPGA SoCs in the semiconductor industry and the forefront of technology. I think you can see that question there, Jeremy.
Yeah. I mean, ultimately, it depends on the application you're trying to do, right? So in some instances, you will do development with an FPGA and SoC, and then you might create an ASIC based on your development. But in a lot of other instances, the flexibility of having an FPGA that you can reprogram in the field as well as the software um, makes it a very viable solution that, again, it all depends on the application you're doing. But I definitely see going forward in the future that, you know, the the amount of flexibility this provides as a solution um, will definitely be needed in future projects.
Excellent. Okay. Well, I think, Chris, is there anything you wanted to add to that or?
No, I think Jeremy answered it well.
Okay. All right. Well, thank you to the two of you. I don't seem to have any more open questions, so I would like to invite everybody that is actually on the webinar. If you have any more questions, please do go and connect with Chris and Jeremy on LinkedIn. Maybe Chris and Jeremy, if you want to post your LinkedIn URLs in the chat there, just while I'm closing up, then everybody can go and follow you. And also stay in touch with Fidus. Keep following our page. We do these monthly. If you have any particular topics that you would like us to cover, we'd be more than happy to bring an expert to the table. So yeah, have a great day, and we will be sending out this recording. As soon as we publish it, we'll edit it and publish it to our website tomorrow. So take care, everybody. Have a great day, and thank you. Bye-bye.